our new session. Our guest is again Dmitry Talalaev. It is a sort of continuation of the previous talk, and we will hear a story about Zamolodchikov tetrahedron equation and relations to integrable systems. Dima, you're welcome.
Thank you. Thank you very much. Do you hear me? It's okay? It's okay?
Главное, чтобы вот этот плохойчик был неподалеку.
Is it okay? Okay, I will start to recall some definitions, and I need to understand to which extent you are familiar with the Yang-Baxter equation.
Well, let us assume that at least I know nothing. I know something, but let us assume that nothing.
Okay, for me, Yang-Baxter equation it's quite mysterious and mythological object. So I will start from the beginning. It is an equation for example, for a linear operator which acts in the tensor product in the tensor square of some vector space, and Rij in the endomorphisms of some tensor power of the vector space V. So it's a linear operator which acts on the if and jth multiplier in this tensor product, non-trivially by this operator, and trivially on other components. So, for example, R12 in for k equal 3 is just R multiplied by the identity operator on the third component in this tensor cube. In endomorphisms of V of the third tensor power of V. There is so here it is the vector version of the Yang-Baxter equation. There is a set theoretical version. It means that R is just a map from V to V, just a Cartesian square of some set X. Let it be X X X X X, and R12 R23. In this case, it acts on three elements, X, Y, and Z, and give X and R from Y and Z, which is a pair of elements from X, and it is a definition. It is a definition in the set theoretical case, but the equation takes the same form in this case, so we can write it. And so the important thing explaining the structural role of this equation is the relation with the braid group. So if R is a solution for the Yang-Baxter equation, for example, in the set theoretical case, and P is
No sound.
Пропал звук.
No sound.
sorry.
No sound.
Is it okay now?
Now it's better.
The map from Sasha Mikhailov, I guess. So the map rho from sigma I, the generator of the braid group, to Si I plus 1 is the representation of a group. So it's a homomorphism. So we can say that it is a representation of the braid group in the set of symmetries of some Cartesian power of X. And that is principally why the Yang-Baxter equation plays a crucial role in the theory of knots, because we can always represent knots by braids, and the representation of the braid gives invariance of knots.
As I plus 1, you modular 3.
No, it's I from 1 to n minus 1. So it's a representation of generators in the braid group up to order Sn minus 1 m. Is it known, or it's better to give some comments on this? So, but it is crucial, and that's why it is interesting to find new solution for the Yang-Baxter equation with some special properties which are in accordance with some additional Rademeister moves in knot theory, because this is just the third Rademeister move. There is a first Rademeister move, which is an additional condition for the representation of the braid group. Another origin of the Yang-Baxter equation, in fact, it is a question of the deformation of some commutative algebraic structures. So in Hopf algebras, there is a notion of quasi triangular Hopf algebra, which is defined by the following property. The co-multiplication in this algebra, it is not necessarily co-commutative, but it is quasi-co-commutative, and this equivalence between delta of A and delta opposite of A is controlled by some operator. And very natural, this operator solves the Yang-Baxter equation.
This is the definition.
Yes, it's a definition of the quasi-triangular Hopf algebra. But exactly, one needs also for R to be a solution of the Yang-Baxter equation for good properties of this deformation. Is it known what is delta opposite of A?
Better recall.
So delta of A, it is an element of the tensor square of the algebra A. So it can be represented by some sum of A F A I 1 and A I 2 sum over A, and delta opposite of A, it is the sum with inverse components AI2, AI1. And naturally, it is not the same as the original co-multiplication.
This is comparison of
Yes, with P. Yes, yes.
You don't like
I like diagrams. But you see here it's a permutation acting on the tensor power, and here it is an element of the tensor square, so it acts differently from just the permutation of tensor powers. And in such quasi-triangular Hopf algebras like quantum universal enveloping algebras, these are universal R matrices, which are composed by some very natural algebraic procedure, and it solves the Yang-Baxter equation, which implies some good properties of this deformation. So philosophically, it is a good way to deform commutative algebra objects. So this co-multiplication is not co-commutative, but it is quasi-co-commutative. Yes. So it appears, the Yang-Baxter equation appears as a good deformation of a commutative structure. Co-commutative, but it's equivalent. So the dual object, the dual Hopf algebra, it has quasi-commutative multiplication.
So if it is commutative in the case when R is identical,
yes?
R is considered as a deformation.
Yes, yes. So it's a good deformation for the commutative structure. What else? What else? So, in fact, I think that by this reason, R matrices solution for the Yang-Baxter equation appears in integrable systems because it deforms some commutative property and produce new commutative families of integrals of some objects which are appreciated in integrable systems. But it's quite a big story. So I started from this point because it's better to know this to define its generalization, the Tetrahedron Zamolodchikov equation.
There's no sound again.
I don't speak. Is it okay?
Oh, yes. Thanks.
Zamolodchikov tetrahedron equation. So for me, it needed a lot of time to be able to take to keep in mind all the indices, all the definitions. But so we will start by just the definition, and I will try to explain how it is managed. So now phi, it is an element of endomorphism of the tensor square power of some finite dimensional vector space V. And we can write the following equation. 5, 4, 6, 3, 5, 6. And equals the product of same operators in the inverse order. Okay. For the Yang-Baxter equation, so it will be here. It is good to have such a picture. One, two, three, and here there is R1, 2, then R1, 3, and here 1, 2, 3, and it is the same as 1, 1, 3. It is not good. 1. Because it is not 1, it is 2. Here 1, and here we have R2, 3. Here is R1, 3, and here R1, 2. The order in this product is described by the order of the possible composition of operators in the nodes of this diagram. So each operator, an operator is associated with such a diagram. We 1, we 2, 1 with 2, and here we place R1, 2, and we can compose such operators if the outgoing edge of one diagram is incoming for another one. So, for example, if we have such a diagram with spaces 1, 2, 3, it corresponds to the product we 1, 2, the first one, and then this outgoing edge of this at this node is incoming for this node, and it means that we can apply here. I'm sorry, R. Is it clear the order of multiplication of such operators? So it's a good picture to keep in mind the indices and the way to apply such operator in a good order. The good way to encode this picture is the tetrahedron. Else with with oriented lines. There are 6 lines here. 1, 2, 3, 4, 5, 6. And this picture corresponds to the following product of operators: 1, 3, 5, 1, 2, 3 here. After this, 1, 4, 5. After this, we can apply this point, and it will be 2, 4, 6. 4, 6, and the last one is 5, 3, 5, 6.
So you assume that indices are ordered from the increasing always.
Yes, yes. And it should be equivalent to to the product applied to the inverted tetrahedron. Inverted tetrahedron, it means that we have to pass one plane through the point of intersection of 3 other planes. So it's like inversion. And it should be something like this. And the good ordering is 2. I suppose it is 5. This is 4. This should be 1. And this should be 6. And by extension, it is 3. So the lines 1, 2, 3 intersect here. So it is 3. And the good way to make a composition of such linear operations is 5, 3, 5, 6 from this point, then 2, 4, 6, 2, 4, 6. After this, it is 1, 4, 5, and the last one is 1, 2, 3. So what is important to say? Okay, I will start from examples. Examples. Lustig example. Lustig. It is a rational map. So we can understand this map as a map on the tensor product of rational functions. So this map act on rational functions on 3 variables. So it can be understood as some completed tensor third power of function of 1 variable. So the statement is that this rational map solves the tetrahedron equation, and there is a very important algebraic problem which is related with solution. It is a problem of parameterizing the unipotent upper triangular matrices. I will call U3 is the unipotent upper triangular upper triangular 3x3 matrices. It means that the matrices of this type. Let U1 of T be a matrix of this form, and U2 of T is a matrix like this. Then almost all such matrices can be represented as a product of 3 x y z, and this can be represented as a product of such elements in 2 ways. My statement is that this rational map is the change of parameterization. It is a map which gives such 3 parameters from this set of parameters. So these are 2 different ways to parameterize almost all.
Represent in 2 different ways.
Yes.
The
relation between.
Initial ones will be related by.
Yes. Yes. And it is quite a general situation. There, solutions of the Zamolodchikov tetrahedron equation appears. So in this case, this can be demonstrated by the following observation. If we consider the unipotent group of order 4, it is 6-dimensional. So an element B from U4 can be represented in such a way: 1 x1, U2 x2, U1 x3, U2 x4, I'm sorry, U2 3x5 and something else. So it's better to write here like this: 1, 2, 1, x6.
Dimension unipotent.
Of the matrix is 4x4 unipotent. Yes, but it is 6-dimensional. A, B, C, D, E, F, and can be parameterized by as a product of 6 1-parameter subgroups. And we can change this parameterization from this one to completely inverse one by applying the map phi in 2 different ways. So that's why this transformation solves the tetrahedron equation. So it's an Okay, it's quite a general phenomenon how the solutions of Zamolodchikov tetrahedron equation appears. So another one. Euler angles. Let our group be SO3, and almost all elements of this group can be represented in the following way. Let V1 be the rotation in the V1 of T be the rotation in the plane XY. And V2 be the rotation in the plane YZ. Then almost all elements are SO3 can be represented as a product of such elements X, Y, and as in the elastic case, it can be done in two equivalent ways: 2 prime Y prime with 2X prime, and there is also phi orthogonal, which maps X, Y, Z to X prime, Y prime, Z prime, and it also solves the tetrahedron Zamolodchikov equation.
Do you mean after rational uniformization of trigonometric function? Yeah.
Yes, it's a solution in some completed space. Exactly. And another solution which is not exactly from the group theory, but it is related with the symplectic group, in fact. So it is called electric solution. Phi electric. It is also a rational map. It's a deformation of the elastic map, and it also solves the tetrahedron equation, and it is equivalent as a map to the star triangle transformation transformation in electrical networks. Yes, by this cubic part. But it also solves the tetrahedron equation. So I'm sure that we have enough examples. So my aim today is to define all the family of n-simplex equations, the combinatorial stuff, which allows to define this set of equations, and to define the cohomological complex, which allows to calculate some invariants of n-simplex solutions of the n-simplex equations.
Dima, before you're going forward, may I ask you a question? When you talk about the Young-Baxter equation, you say that it is a representation of the braid group and also related to the Hopf algebras, deformation, etc. Any similar interpretation for anything useful about the Zamolodchikov equation? Can you say any relation to representation theory?
So, Sash, you know that philosophically it is related to two knots, to braids, and it can be done quite formally as a functor from the two braided category of two tangles to sets to vector spaces. Yes, there is such good language, but the two braided category, it is a two category, so the world is a little bit more complicated.
May I also ask you a question before you continue?
Yes.
Right. So you have a previous work on using Zamolodchikov equations solutions to produce invariants for two knots, but it turns out only be quasi-invariant. I wonder if there's any updates in that direction.
I'm not quite understood, but you asked about invariance of two knots.
Yeah, but you only got a quasi-invariant of two knots.
Yes,
right? It doesn't.
It's always on this point.
Right. So, do you have any updates in that direction?
No. The problems are important. So we have no other results, but we work in this direction.
Okay. Thanks.
Yeah, may I add a comment, please?
Sure.
This concerns the first question about the relation between Young-Baxter and Tetrahedron equation. I mean, it's well known that whenever you have a system of Young-Baxter equations, this implies a solution of the tetrahedron equation. Or you mentioned this example, or you gave this example of a parametrized Young-Baxter map. So what one also calls a localized Young-Baxter equation. This automatically then implies that the parameters satisfy the tetrahedron equation. I think this should be the answer for the first question, if I understood it correctly.
I'm sure that the local Young-Baxter equation implies the tetrahedron equation if we have something like the unique decomposition in this 6-element product, which I presented in the Lustig case. In generic situation, I'm not sure that it is automatically true.
Certainly there should be some technical condition, but the scheme is clear and it holds throughout all the simplex equations. So the n+1 simplex equation is obtained from a system or from a localized version of the n-simplex equation. This is the relation between the kind of which is also sometimes called integrability. So somehow the integrability condition of the n-simplex equation is the n+1 simplex equation.
I couldn't add something else. So it smells like some additional integrability condition, but at the present I have no such statement that all solution for the tetrahedron equation comes from some local Young-Baxter equation.
No, probably not. Not all of them. This is one method to produce solutions of the tetrahedron equation. And this is a method which has been used in many papers.
That's right. Yes. So there is such relation, but I could not say that it is a generic.
Sorry for disturbing you. I mean,
no,
I think
it's
it's
okay.
better you go on with your program.
Before you go on, may I ask one more question? This Young-Baxter equation has solutions depending on parameters, and all solutions you show us for tetrahedral equation don't have any parameter. Do you know any solutions which depend on parameter?
No.
So how you can then proceed to higher dimensions in this way?
It's an open question. Very good open question.
Well,
Okay.
maybe we shall postpone discussion until the end of the talk.
Okay. Okay, we continue. Hypercube combinatorics. So we will consider just the n cube, and all faces of this cube can be encoded by such sequences of symbols. 1 star star 0 star star 1 star star 0 1, for example. It is a 4 face of the 8 cube. Star means that such a component varies between 0 and 1. And here 0 means that this component takes the value 0. Yes, these are fixed, and these vary in the interval. So it's a good way to control all faces of all orders. And we will need also some notion of incoming and outgoing subfaces of some face. And for this, we introduce a sequence of alternating zeros and ones, etc. And we will say that definition. Let is the k face of En. We call the sigma I. It is a face with the eth star replaced by some symbol. Symbol S means that it is the sigma with eth star replaced by S. Example, let sigma be star star star, which is the free face in E3. Then E1 0, it is the face 0 star star. So 1 is the star, 1 star. So definition. Sigma I eta I called incoming phase, incoming k-1 phase of sigma, and sigma I. There, the ith place is replaced by the inversion of the sequence element in the sequence.
Just a moment.
Mhm.
So we fix the length of sigma, yes?
It is
It is K.
yes, yes.
So, and these two indices control the place and the meaning
The place of the star and the value.
and the value.
And if we take the value in place of the ith star, which is the element of this sequence, it is called the incoming subphase. And if you take in the alternating sign, it is the outgoing subphase. K-1 subphase. Let us consider examples. So it is the E2 cube. 1 0 1 0 0 0 1 1 1. It is star 0 0 star 1 star and star 1, and this two phase is star star. Let us consider this phase and these four subphases. There only one star is replaced by a symbol. If we replace the first star by the first element of this sequence eta, it is an incoming subphase. So this is an incoming subphase, and this is an incoming subphase, because we replace the second star by the second element of the sequence. And we will, so principally we will apply an operator R to some variables which are attached to the incoming subphases of this cube. Okay. And principally, if sigma is a k phase, it has k incoming k-1 subphases and k outgoing k-1 subphases. Let us consider some set, a set, and R is a map xk to xk. We'll define a set of admissible coloring of k-1 faces of the cube definition. Faces and k-1 a n is map to x. C is the map from the set of k minus 1 faces of En to the set X. It's called admissible. Admissible if for each sigma which is k face of En. The colors means the values of this function on the colors of incoming k minus 1 faces of sigma and outgoing k minus 1 faces of sigma means that C1, Ck, and C1 prime, Ck prime are related by this map.
So this C is a subset of
C
no
C is a map
it's a map
from k minus 1 faces to some set X.
Yes.
So we call them colors of k minus 1 faces.
Color is the value of
No, yes,
the
yes.
yes?
Mhm.
Mhm.
So, for example, if k is 2, k is 2, n is 3. So this is some cube, first, second, and third direction. This allows to define for each two face what is the incoming and what is outgoing one faces. For example, this face here, it is the face with the second variable 0. So it is star 0 star. This face. The incoming subfaces, one subfaces of these two face is 0 1 star. 0 1 star. It is this one. Oh, 0 0 star. And 0 star 0 1 star 0 1. It is this one. Star 0 1. There is also a lexicographic order on these incoming faces. So so it is numbered by the place which is replaced by the symbol. So it is the first one, it is the second one. And for these two faces, we ask that variables here C1, C2, C1 and C2 2 prime that are from C1 C2 is equal to C1 prime C2 prime. So it is a condition for the admissible coloring of of edges on the free cube. On each two face, we place a map R, and we allows only such coloring of edges that the colors of incoming edges and outgoing edges related by this equation. But we ask such equation for each two faces of this three cube. In this case, partial statement. This set of conditions for admissible coloring is good. So there is solution for such problem. This definition is compatible. Problem of admissible coloring k equal 2 n equal 3 is compatible if R is a solution of the Yang-Baxter equation. Compatible. You see, we can try to color. For example, we can start from some initial set. In this notation, I suppose that it is something like this. And starting from this, we can try to color all edges of the cube. But the edges which are on the other side, this one, they can be colored by two ways. Yeah. And it is a necessary condition for possibility of admissible coloring of two of edges of a free cube. And this compatibility condition is exactly the Yang-Baxter equation.
The first question is why admissible, non-trivial admissible colorings do exist?
It's equivalent question. So if R is a solution of the Yang-Baxter equation, all admissible colorings are parameterized by the colors of absolutely incoming edges of this three cube. In this cube, there are three edges which are incoming for all two faces. And this condition says that starting from this initial three edges, we can color all other edges and in a unique way. So this is a compatibility condition for the possibility and for the uniqueness of such
multi-dimensional used by induction.
Yes.
Using this statement.
Only this statement. And it is the same for all n. For the k equal 2, we can color all the edges of the n cube, just imposing the Yang-Baxter equation for this local law of admissibility of a coloring. So the statement in principle is that the only condition for this coloring is on the k+1 faces, and there are no other syzygies. Okay, I'd like to formulate the generic statement. the coloring problem coloring problem Kn is non-trivial if and only if R solves an equation in some ek plus 1 cube. So it's sufficient to impose a condition on R in ik plus 1 cube. I will write this equation in generic situation. Is non-trivial, solves an equation. In this case, all admissible colorings are completely defined by colors by any colors of absolutely incoming k minus 1 faces. Let us show what are the absolutely incoming faces in the case. Sorry.
For me, well, the number of colors is the
Is
number of
X.
elements in X,
Yes.
and all your results does not depend on.
Yes, but the equation, this equation depends on X. I have not yet written an equation, but I said that it is defined completely in some k plus 1 cube. This is the only condition. All other continuation is automatical.
Colors is included with the R.
Yes, and here you may take whatever you want, what color you want of the initial of absolutely incoming edges, incoming faces. One, two, three. So what are the absolutely incoming faces? One faces. I suppose that they are of such form. Okay. These one faces, they are boundary faces of some two faces. Absolutely incoming faces are such that they are incoming for all two faces for which they are boundary faces. I suppose that these are absolutely incoming faces, because this one face can be a boundary face for some face there in the first places we have star, and in both cases star is replaced by 0, and it is the first star. So there are two faces for which this is a boundary face, such and this and this. In both cases we replace the first star by 0. in this picture, there this one, it is 0, 0 star, 0 star 1, 0 star 0 star 1. It is this one. And star 0, 0, star 1, 1. It is star 1, 1. I suppose it is this one. Starting from this absolutely incoming edges, we can color all one edges if R is a solution of the Yang-Baxter equation. I will try to make it. So the first coloring is to obtain such colors. Then we color this and this. And the last one is by this process, we obtain the colors of absolutely outgoing edges. These one are absolutely outgoing. But we can get the colors of them by the other part of this cube. This one, and like this to get this one. The only conditions are on the absolutely outgoing edges, and it is the condition of the Yang-Baxter equation. But here we can place all colors from the set X. Okay, now I need to write an equation. An equation on the faces, on the k faces of this k plus 1 cube. It is written like this: phi 0 star star star. One star. I'm sorry, it is in verse phi 1 star star 0 star, like this.
Well, what is the next?
Here.
For example, you have 0 stars, star 1 0. What will be the next? I cannot guess.
So here are the faces of the k plus 1 cube. We replace one of the stars by 0 or 1. But here they correspond to the incoming k faces of the k plus 1 cube. And here these are the outgoing k faces of the k plus 1 cube. And we have to apply them in such a direction. This equation is called n-simplex equation, k-simplex equation. And it is this equation in the theorem. Okay, I'd like to work a little bit with this notation to demonstrate that it is the same thing as the Yang-Baxter equation in the k equal 2 case, and the Zamolodchikov Tetrahedron equation in the k equal 3 case. And then I'd like to propose you some interpretation why it is called simplex equation. Okay, for in the case k equal 2, we have here 3 symbols. So it is phi star 0, phi star 1 star, phi 0 star star, and it is equal to phi 1 one. Such a map means that in our cube it is applied on the bottom on the bottom two face of this cube to the colors of incoming edges to get the colors of the outgoing ones. R12 because it is applied to the argument in the first and second direction. This map is the same as this one, but it is notated here that it is applied to the variables on the edges of the different face. So it is also R12. So principally it is R12, R13, R23, 1, 3, R12. But it is not so simple in the case of k equal 3. What should it be? It is phi 0 star 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 1 star star 0 star phi star 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 1 1. If you remember, in this case, phi is applied to colors of two faces. It was a map phi. It is a map of x power k to x power k. Here it is the colors of k minus 1 incoming subfaces of incoming k minus 1 subfaces. So in the case of a free cube, but here k equal 3 and I equal 3, phi is a map from colors of some attached to two faces, from free two faces, free incoming two faces, and which produces colors of outgoing two faces. So in this case, phi is x3 to x3. And this x is the color of a two face of a 3 cube. Okay. To obtain a tetrahedron equation in the traditional way, we should replace this notation by a map which acts on colors on two faces. Let us number the two faces of a 3 cube. Of a 4 cube. We have here a 4 cube, several free cubes, 8 free cubes in a 4 cube, and two faces in such 3 cubes. So we need enumerate two faces of a 4 cube. The two faces are like this. And I'd like to enumerate it in the inverse order. What is written here? What does it mean? What does it mean? Phi applied to the first 3 cube in the 4 cube. Here it is applied to the direction 1, 2, 3, but we need to enumerate the 2 direction in this 3 direction. And due to our notation, we have here the 2 dimensions 1, 2, 1, 3, and 2, 3, and the have numbers 3, 5, 6. So phi star 0, it is phi 3, 5, 6. So by this dictionary we can apply, we can obtain the tetrahedron equation. But let's verify. Here it is the direction 1 to 4, and 1 to 4 means the 2 direction are 1, 2, 1, 4, and 2, 4. And here is 2, 4 is 2, 2, 4. So we have 5, 6, 2, 4, 6, 1, 1, 3, 4, 1, 3, 1, 4, and 3, 4. And it is 1, 4, 5. 1, 4, 5. And the last one is 2, 3, 4. 2, 3, 2, 4, and 3, 4. It is 1, 2, 3. So it's the same notation as the Zamolodchikov tetrahedron equation, but in terms of the numbers of 2 direction in a 4 cube. Do you need some comments?
Let's ask the audience. Sasha, any comment?
Dmitry?
Yes.
This reminds me very much of Brühar order, where you also have these 2 ways of numbering. You number the spaces by
Yes.
space 1, 2, 1, 3, 1, 4, and so on. And on the other side, you can also number the positions of spaces in a row on which the map acts. And this seems to correspond exactly to your change of numbering here.
I'm sure that it is exactly related with the Manin-Shechtman higher-Breuer order. Yes, yes, exactly the same thing.
More questions or remarks? Well, then let us proceed.
Okay. Just a comment why this equation is called the K-simplex equation. So with this coloring procedure, we can relate a graph G I K G K. It means that we color K K minus 1 faces in a K plus 1 cube. I'd like to consider such a graph. Graph this such marks. So the vertex K faces of the K plus 1. Edges K minus 1 faces of they are oriented edges, and we have sigma K minus 1. It is an edge of this graph if K minus 1 incoming for omega K in V and outgoing for some omega sigma delta.
This is oriented.
Oriented because
The arrow is from incoming to
I'd like to say that if some edge is outgoing for one face and incoming for another face, when we connect such vertices by an oriented edge. You understand this edge is outgoing for this for this face, incoming for the next one. Then in our graph we have vertices corresponding to these K faces and an oriented edge which is dual in a sense to this K minus 1 face. So the statement is that this graph has two components. G K plus 1 has two components. Which are K simplices. On vertices. for one simplex, and there is an order. So there is an edge between such vertices. It is obvious because we have a face like this, and it is outgoing for this face because we replace the first star by 1, and it is incoming for this face because we replace the first star by 0. So in this sequence, we have edges like this, oriented edges. And this simplex is oriented in inverse order, like this.
Two connected.
Two simplexes,
Mhm.
just two simplexes,
Mhm.
and the two components of the condition of the n-simplex equation are related to two such simplexes. And this graph it described how they are composed, such maps. An arrow here means that we can compose maps, and to obtain the colors of the absolutely outgoing faces, starting from the faces of the absolutely incoming ones. And there are exactly one ways to do it, and it is exactly related to the higher Brillouin order. Okay, so how much time?
Yeah. Well, 16 minutes.
Okay, so it's a good period to define the cohomology complex, which is now quite simple to do. So let phi be a solution of K simplex equation. That means that it controls the coloring problem of K minus 1 faces of some of big cubes. So C K n is the set of admissible colors with values in X, set of admissible R admissible colorings of K minus 1 faces of I n cube with colors in the set X controlled by a map R. I'm sorry, phi. Then there is so, and we can see a complex now. See n with all these values X, phi is just the vector space, the K module generated by the set. K is a field. CK n X phi. Just a vector space generated by a set. So it is a set.
Okay.
Okay.
Mhm.
And we can define boundary operator delta, which goes from Cn kx phi to Cn minus 1 kx phi. We can just consider the coloring of boundary of this n cube with alternating signs. So delta of C is the sum of restrictions on ith incoming boundary minus C restricted to the ith outgoing boundary.
C is a color.
Yes. Do you want an example? Let C be a coloring of one edges of the free cube. So it corresponds to K equal 2, N equal 3. We can restrict this coloring to the two faces of this free cube, and there are 6 two faces, 3 incoming and 3 outgoing. We can just consider this linear combination of coloring of the small cube with alternating signs. So it's quite a natural idea, just the cubic analog of the simplicial complex.
Yes. Yeah, I just wanted to say this. So this what we are going to construct will be homologies of
Homology.
solution.
Yes, homology
Will be related to phi.
to phi, exactly, to phi and x. And the cohomology are defined by the dual map. So we can consider the dual spaces to the C x phi. Let it be okay. I know simplicial complex n. And the differential here is from CCN to CCN plus 1.
Just the dual map.
Just a dual map, yes. Let us consider the simple case of k equal 2, n equal 3, and what is the Tuka cycle of the complex related with the solution of the Yang-Baxter equation. So it's a function on coloring of two cubes of rectangles. Admissible coloring of two cubes, they are controlled by two colors. So what is this? N equal 2, and we have to calculate the inverse map to this boundary operation. So what is the coloring in this case? there are two incoming edges, and there is a map R. So all admissible colorings are parameterized by two colors of incoming incoming edges. So all admissible coloring in this case are just two colors. X, Y, X prime, Y prime. Here, you remember there are absolutely incoming faces, and there are different ways to color absolutely outgoing faces, one faces. And there are some colors of additional of other edges during this process. I suppose that the good condition for this differential is the following one. So phi from x, y is a Tuka cycle. If phi x, y, y, x,
So, in the sense, this is an equation on double tilde letter. Yeah? We compute
we computed phi on different on two faces, on 6 two faces of this free cube. In each case, phi on the cube, it is some function only on initial values, because the colorings are parameterized by initial values. And this part is attached to incoming faces, and this one to the outgoing faces, two faces.
seems strange to me that the condition of phi is highly nonlinear.
Yes. It is not nonlinear because we have taken an exponential. So it's a product here. But product, one product is equal to another product. If you take a logarithm, it is a sum of such minus the sum of these expressions. So it's some exponentiation. So it's a linear object, but exponentiate.
So
this is a condition for the Tuka cycle of the Yang-Baxter
boundary.
Boundary. I think it's not very good in this small dimension. So maybe it's all trivial. So you see, it is not it's not good to consider the coloring problem on one cubes.
It's trivial.
It's trivial.
Yes. But nevertheless, yes, of course, it is somehow senseless, but we should define a boundary.
okay, so what is the boundary? If we have a coloring of a for cube, we can take the sum of incoming colors and difference of outgoing colors. So it's a little bit late for this calculation. I'd like to give you examples of the Fricka cycle of the electrical solution of the tetrahedron equation.
To understand,
Uh-huh.
what will be the invariant meaning of these cohomologies? What would mean, for example, that they are trivial? Assume that we computed them for some dimension and found out that they are trivial. What does it mean in terms of
Do you remember
solution?
in my previous talk, I constructed solution of the vector Yang-Baxter equation, starting from the set theoretical Yang-Baxter equation, and it took a cycle. So in effect, it's a way to centrally extend the set theoretical solution of the Yang-Baxter equation.
To extend to vector.
Yes,
vector.
yes, yes.
Okay. Okay.
For example, for the electrical solution, by electrical, it means that x, y, z is mapped to x, y.
Why is it electrical? Because it somehow relates to
Yeah,
circuits.
star triangle transformation in electrical circuits. No, it's very interesting. I will tell you. X plus z, x, y, z, and the last variable y, z, x plus z plus x plus x, y, z.
Deformed Lustig solution.
Yes, deformed Lustig solution. And so now Fricka cycle is a function on the coloring of a free cube. We have x, y, x, y, x, y, z. The colors of incoming two faces, x prime, prime, z prime, the colors of outgoing faces. And Fricka cycle is a function on this coloring. So phi is a function x, y, z, s prime, y prime, z prime. And it is just a calculation that phi equal to y and phi equal to y prime are Fricka cycles of the tetrahedral equation, of this tetrahedral equation. I understood. So phi is a co-boundary if it is a function from x, y, f x prime, f y prime.
In this case.
Yes. Tilde, sorry.
Yeah.
exactly the sum of incoming minus sum of outgoing in this exponential
Yes,
form.
of course. Yes, of course.
Mhm.
Mhm.
So it's quite
Yes,
natural.
yes,
Mhm.
natural.
Mhm. Okay, do you want as the last sentence the relation of this
Yes.
transformation with the star triangle transformation in electrical circuit?
Yes. Yeah. If I remember,
Sufficient. Yes.
But when you are clearing the board, you said nothing about integrability. You promised.
It's another story. Uh-huh. So it's a statement. If you have two electrical circuits, which are the same except this small local region, then there is a transformation, not phi, but say S, 1, 2, 3. Which makes this electrical circuit electrically equivalent.
Electrically what?
Equivalent. It means that if somehow we have sources of potentials, and they are the same for two such circuits, then the currents will be the same.
So we mean these are elementary equivalence transformations
Yes.
of circuits.
Yes. And this transformation, after some small exchange of variables, produce such solution for the tetrahedron equation.
And is it true that any equivalence is composed of such elementary ones?
Almost.
Oh.
Yes. There is some condition of criticality of the graph of electrical circuits. If they are critical and equivalent, then they are related by the finite number of such transformations.
Well, I think that we have to finish for today. So we had another proof of the fact that mathematics is a beautiful science. We have some 5 or maybe more minutes for discussion. Does anyone want to comment or ask a question? Volker, do you hear me? Кость, at least you. So no question, no comment. Then Dima, thanks a lot. And I think that we still have another talk related to integrability problems. Yes, thank you very much. So the next session, we shall have a talk by Valentin Lechagin, and in 2 weeks there will be a very small workshop dedicated to the 16th birthday of Maxim Pavlov. Everyone is invited. See you.
See you soon.
See you.
Sorry? Yeah.
Thanks a lot.
Thank you. Well, See you in a week. Thanks a lot. Goodbye.
Bye.